So it is my pleasure to welcome Kiersten Boley, who is a NSF Graduate Research Fellow at The Ohio State University. Her research broadly focuses on the impacts of elemental abundances on planet formation and the influence of volatiles on planet structure and evolution. And aside from her research, she is actively involved in DEIA efforts and public outreach programs. And as we were just talking about, she is one quarter of the grad student-led astronomy podcast, Astro Soundbites. So everyone should definitely download that and listen to that, which breaks down current astronomy research for undergrads and the public. So it's my pleasure to welcome Kiersten. Here you go.
Thank you. Yeah, hello everyone, and hello everyone online. So yeah, I'm going to be talking a little bit about, or a lot of it, about my research today. So I sit in this kind of weird interface of observation and some theory work. So we're going to get into a bit about planet demographics and also some interior modeling that I've done. So starting off strong with the demographics, one of the questions that I try to answer with my research is, when did the first planets form? And for those of you that may not be aware, the reason why we know that planet formation could not occur throughout the history of the Milky Way is because we know that the first generation of stars within our galaxy were metal poor, which means that subsequent generations of stars had to be born and die before there was enough metals within the interstellar medium for it to be enriched enough for planet formation to begin. But another way of asking this question is to kind of rearrange it to instead ask how much material is required for planet formation. And there's actually quite a rich history of looking at this question of how much metal is required for planet formation. And so back in 1996, there was this wonderful paper that was submitted. And with 4 planets, we said, this is a great time to start doing some planet demographics. And so this result still holds up today. It's a wonderful paper that spurred on this idea looking at how host star metallicity corresponds to giant planet occurrence rates. And so several different works and theory papers were published trying to figure out what this critical metallicity limit is that causes planet formation to begin within our galaxy. And so from these studies, we discovered a couple of different things. So we learned that host star abundances are an excellent proxy for the available metals within the protoplanetary disk at the time of formation. And we also found that planet formation begins somewhere between -2 and -0.5 metallicity. So this is what the theory predicts. And I'm going to highlight this because you're going to be tired of me mentioning these numbers, but -0.5 metallicity is where we think that planet formation could begin, so this range. Now, observationally, several different studies looked at this question as well. So what you're looking at here is giant planet occurrence rate on the y-axis, and on the x-axis, you're looking at metallicity. And you're looking at several different works trying to constrain this function. And so the data that they were using looked a little bit like this. So this is just the giant planets discovered before 2010. And what you'll notice already is at -0.5 metallicity, the data stops. We didn't detect any planets below this point. And this is partially due to the way in which we create these surveys. So several different studies ended up trying to constrain this more metal-poor region, including one of my own works that looked at hot Jupiter occurrence rates around halo stars. But what's important to note about these studies is that we did not detect any giant planets. So these are great upper limits. And with my previous work, we were even able to roll out one of these models. In terms of small planets, though, we see a slightly weaker trend. So on this plot by Pettigrew et al. 2018, you'll see in green and in blue super-Earth and sub-Neptune occurrence rates as a function of metallicity, and they are significantly weaker than the Jupiter and the sub-Saturn occurrence rates, which are shown in red and yellow. However, since the study was done using Kepler, once again, we're above this metallicity limit in which we think planet formation cuts off. So we aren't able to get after this question of how much material is required for planet formation. And I'll highlight one more work by my colleague John Sink that combined Kepler and K2 data. So K2 data is important here in this context because K2 was able to look at a wider variety of stellar types than Kepler. And so what we see here isn't drastically different, but for the super-Earths and sub-Neptunes, we see a little bit of a weaker trend, actually, with metallicity. And for the Jupiters and sub-Saturns, we end up seeing basically the same trend that we see with Kepler. And so once again, we're above this metallicity limit where we can start to probe this question of how much material is required for planet formation. But from what we see from K2 and Kepler, it looks like that the super-Earths and sub-Neptunes are going pretty strong in terms of the metallicity limit. So this is where TESS comes in. So TESS, given that it's essentially an all-sky survey, is really advantageous to look at this question of when did the first planets form and how much material do we need? Because it's able to look at a wide variety of stellar types and galactic locations. And so we're actually able to get after this question with very large sample sizes. So I'm going to talk about two samples that I've looked at, and I'll start off with the first. So I constructed a sample using spectroscopically derived metallicities that were below negative 0.25. And I'm going to put an asterisk here because you're probably already thinking, she keeps saying negative 0.5. Why are we talking about negative 0.25 now? The reason why we chose negative 0.25 is so that we can compare it with K2 and Kepler data. So we want to get an idea of any sort of systematic biases that we're going to see with TESS compared to Kepler. So this is a way basically to correct for that. And then we wanted to look at FGK stars similar to the TESS, similar to the Kepler surveys, so that we can accurately, compare apples to apples instead of apples to oranges. And then lastly, we wanted to make sure any planet candidates that we did find that we could follow up observationally. And so what you're looking at is our stellar sample in the plot to your right, and basically the subsample. So in total, we had around 110,000 stars that we searched for planets in. And of these around 110,000 stars, 23,000 of them were within this regime that we can compare to Kepler and K2 data. So I'll briefly walk you through the methodology and how we get to these occurrence rates. I will try to be brief. But basically what we do is we get these full frame images, and then we optimize the light curves for planet transit searches. So what that looks like is doing some sigma clipping. So sometimes you'll have these peaks at the end of observations, and you need to clip those out. And then we'll also do some detrending. So taking nasty looking light curves that look really jagged to basically looking straight, like straight light curves with nice dips that you'll see. And so once we've done that, our light curves go into our planet detection pipeline. So basically what this does is it detects planets. So we use a transit search algorithm to do that with. And from this sample, we were able to get quite a few planet candidates in a variety of different planet types, which was great for the study that we're trying to do. And then on the other side of things, we need to make sure that we get our search completeness, because that's a crucial part of determining our planet occurrence rates. So we do injection and recovery tests. So what this means is we inject synthetic planet signals into every single light curve multiple times to basically have a map of that one light curve, basically, a detection efficiency map for each light curve. So once we do that, we get the detection efficiency, and then if we combine this with the geometric transit probability, which basically just says the further out a planet is from its host star, the less likely we are to detect it, then we get our search completeness. So with the search completeness and the planets that we've detected, we can start to get after these occurrence rates. So the way that we do this is we use a forward model, which relies on a Bayesian framework and a Markov chain Monte Carlo. And so I'll walk you through an iteration of what this does, because I personally find it fascinating, and I never knew what a forward model was until, having to actually create one myself. And so basically what we do is we generate a synthetic population of planets that can look anything like this. So this is super Earth, what you're looking at here, and that nice curved line feature that you're seeing is the Ho and Van Allen relation. So basically, we generate some sort of synthetic population that can look like anything. And then once we have that, we determine the likelihood. And what I mean by the likelihood here is basically we can compare what we get out of the synthetic population. So basically we say we have our detection efficiency. What does this population spit out? And so we compare that to what we actually observe to figure out how well these two populations fit. And then once we have that, we basically adjust the population variables. Since it's an MCMC, you basically walk around. And so adjusting the population variables can look like changing the period to something that looks a bit more like this or like that, and maybe changing the radius as well as the orbit orientations and things like that. So basically, we adjust these variables, and then another population of planets is generated. So this loop continues until we have constrained the planet occurrence rates. So, did we discover the metallicity required for planet formation? So I'll start off with the super Earth occurrence rates. So with K2 and Kepler, we expected to find around 68 planets below -0.5 metallicity. We detected 0 super Earths below -0.5 metallicity, which is quite fascinating. And so I'll show you what this looks like in plot form. So here what you're looking at is the K2 and Kepler data points, and then the Kepler and K2 trend extrapolated out to lower metallicities. So I can put my data points on here for the first bin. And since we have planet candidates and they're not confirmed, I have an upper limit, which is the triangle, so assuming all planet candidates are false, and we have an actual occurrence rate assuming all the planet candidates are real. And so you'll see that whether all of them are false or all of them are real, they agree pretty nicely with the K2 and Kepler results. So we're not seeing any sort of systematics here. And then I'll add our upper limit here. So already we kind of see this dip in the occurrence rate. And this dip is actually a little over a 5 sigma difference between what we expect from Kepler and our upper limit. And our upper limit is a 3 sigma upper limit as well. And so once you start to look at this and kind of calculate the total trend of the occurrence rates, you'll get a function that looks a little bit like this in the green. So we see this pretty huge drop-off in occurrence rates for this more metal-poor regime, which is a good indication that the theory probably is pretty correct, and whether or not this is the exact point at which planet formation cuts off, we're certainly seeing a decrease, at least for the super-Earths, in planet occurrence rate and their requirement for materials. And we do have a couple of other different planets, planet types that I'll talk about briefly. So we're also finding some interesting things for the Jupiters. So for the Jupiters, once again, we have pretty good agreement with Kepler, but we also see that they're a bit shallower than K2 and Kepler would predict. And this is the same for the sub-Saturns, a bit more shallow than K2 and Kepler would predict. And then for the mini-Neptunes are the only ones that agree pretty nicely with what K2 and Kepler would predict. So this has several implications. So the first of which is, A, that we see a distinct metallicity cliff for the super-Earths, which this is by itself very interesting, but if you combine it with what we're seeing with the other planet populations, you'll notice that the occurrence rates, although I didn't stay very long on those slides, they fall all between 0.1 and 1%, which means probably that it's difficult for all planets to form within this regime, and it could have implications for planet formation models. And then the other implication is that we cannot extrapolate or assume that metal-rich, that what we are detecting within metal-rich regimes are the same for these metal-poor regimes when planet formation is expected to get pretty difficult. And so abruptly kind of shifting over to this other population that I've been looking at, it looks a little bit more at, once again, metallicity, but also it includes a little bit more of the dynamics. So looking at a halo star sample, which was kinematically selected, we were able to get stars that fell within this regime of -2 to -0.6 metallicity. And this sample was a decent bit smaller, around 17,000 stars. So from this sample, we were able to get quite a few upper limits for planet occurrence rates in this regime. And we did not detect any planets for any planet types here, which is quite interesting because as you saw before, we were seeing for that other sample that we had no kinematic selections, that we were seeing some sub-Saturns and Neptunes and things like that. So this could be a question of how much dynamics as well as abundances play within planet formation. So looking at Adebekian et al. 2012, you'll notice something pretty interesting here that they're finding. So they were looking at planet occurrence rates where they were looking at thin and thick disk as well. So what you'll see here in the black dots are just stars in their sample, and then the blue and the red dots are small planets and giant planets. And this black curve you'll see, and you'll kind of see it already before I even show, but you'll see this upward trend with alpha element abundances, which is quite interesting. And could have implications for what we're looking at. Is it dynamics involved that's kind of driving this difference that we're seeing between, our halo star sample and, the sample where we don't actually have any sort of dynamical selection? And so with our sample, this halo star sample, it's really interesting here because with halo stars, since they're generally pretty old, you have a decent bit of alpha enhancement as well. And so you would expect, if alpha elements are the main driver here, that we would have detected at least a few planets. So looking at this region here, this more metal poor region that the Atabekian 2012 looked at, we can plot some known planets that have these low metallicities. Unfortunately, there are very few planets that are metal poor around metal poor stars. So we've only got 2. And you'll notice they're also alpha enhanced, at least the ones that we were able to get abundances for. So this further drives this question of how much do dynamics play, how much do abundances play in terms of planet formation. And so I will, with those questions that I'm still thinking of, and I'll kind of leave this demographic section here and let you ponder upon that, because this is something that I've been thinking about a lot in terms of postdoc applications, and transition over to looking at rocky planet populations and the impact of volatiles. So, from the planets that we've detected so far, we see a lot of different populations arising. And there's this population down here of these small planets that are close into their stars, and they may be likely lava worlds. And so the question here is about what's going on with this population. How do what happens within their interiors? How do volatiles impact these planets? And so when we're thinking about characterizing these lava worlds, we have these strange planets like 55 Cancri E. And if we assume that they have magma on their surfaces, we start to ask the question, how much does magma actually impact the structure of these planets, as well as how does the magma composition impact the observable properties of these planets? Because volatiles readily dissolve within magma. However, magma also has a very interesting property where it is less dense than rock at, surface pressures, but it's also highly compressible. So in theory, maybe you could have a puffed up planet like 55 Cancri E, or you could also have a really dense planet. However, there aren't that many studies looking specifically at lava planets, which we don't expect to have thick atmospheres that are large enough to inflate the radius of these planets due to stellar irradiation. So we also know a couple of things about super-Earth compositions as well. So we know that host star abundances, once again, are a great proxy for the available metals and therefore the bulk density of a planet. And what you're looking at here on the right is density, planet density, as a function of radius. And you'll see a variety of different planets on this plot, and you'll see this purple line. So this is the nominally rocky planet zone. So if we were to assume that you can scale up Earth, this is kind of the curved density that you would expect Earth to look like. And so as you can see, most planets don't fall into this nice Earth-like, nominally rocky zone. So the 2 caveats are the ones that fall above this line, so that are more dense than we would expect, super Mercuries, and then we've got these low density planets. And so one question we can ask is, why do these planets have such low densities? And if you think that magma could be causing it, or you could think that maybe the atmospheres could be causing it. So you've got 2 explanations. The first one is atmospheres, and then you can also look at the interior compositions. So here, for these lava worlds, we would need to look at the interior composition because we don't expect the atmospheres to be large enough to inflate the radius to where we get these low-density planets. So you can either look at magma or you can start changing, the amount of iron or changing the amount of iron within the planet as well. So what we ended up doing was creating a planet interior model within exoplex. So we have exoplex, it's a thermodynamically self-consistent planet interior modeling software. And within this magma ocean module, we included a variety of different melts. So we had an anhydrous magma with no volatiles, a hydrous magma with water, and a carbonated melt, which has CO2. And the reason we chose water and CO2 is because they are expected to be outgassed within the planet evolution cycle, as well as water is it's a sticky thing and it likes to get into everything. So within this magma ocean module, we include melting curves, but specifically we include ones that are a bit different than some other works that look at NGSI-03. We choose to look at peridotite, which is closer to the rocky material that we see on Earth, because pure minerals like bridgemanite or NGSI-03 are less likely to form just within the protoplanetary disk. So we chose to look at peridotite specifically. So what ends up happening when we add magma to our models? So we found a couple of different structures for these lava worlds. The first one is when the mantle is fully molten. The second one is when we get a surface magma ocean. And then the last one is this interesting sandwich-looking structure where we have a magma ocean on the surface, rock, and then a basal magma ocean. And we call this a MOSMO structure, so magma ocean, solid rock, magma ocean. And looking at this phase diagram, I say in quotation marks, we have a mass on a y-axis, and on the x-axis you're looking at temperature. And you'll see that depending on the temperature and mass of the planet, you end up getting different spaces that these structures can exist in. So for the surface magma oceans, you're looking at any sort of mass really and low temperatures. And then this MOSMO structure, you're looking at these dense massive planets at higher temperatures, and then fully molten, generally lower masses, high temperatures. And so thinking about the density of the planet, an observable property that we look at often, we wanted to compare this with solid planets. So what you're looking at on the x-axis is the difference in density between a lava planet that includes magma and a solid rock planet as a function of mass. So this region down here means that the planet is less dense than an equivalent mass solid planet, and this region up here says that it is more dense than an equivalent mass solid planet. So you'll immediately see that for low mass planets, we find the biggest density decrease, and for these more massive planets, particularly for anhydrous and carbonated magma, we end up seeing that the planets become denser than an equivalent mass solid planet. And for this module that has hydrous magma, since water is not compressible, and you get some interesting things once you start pushing past this mass limit, which require more dynamic modeling than we included in our model. So we were only able to look at that particular mass. So if we were to look at one planet by itself and look at what's happening within the mantle, what you see here is the planet's surface in gray, and then as you go down the y-axis, you're going deeper into the planet's interior. And then the x-axis, once again, is temperature. So as you increase a planet of constant mass, and we're looking at a 4-Earth mass planet here, you'll notice that the depth of the magma ocean at the surface increases as you increase the temperature. And then you see this interesting structure down here where you end up having a magma ocean form. this basal magma ocean form. And so you'll notice that it happens over a pretty short range of temperatures, at least for this 4-Earth mass planet. And then we can look at the bulk density as a function of temperature as well, which it has this very strange feature in the center. So once again, as you increase the temperature, you see a decrease in the bulk density of the planet. And then you have this region where you get this spike. And so we can pop this out, and then we can compare it to the last figure. And you'll notice that this increase in density corresponds with the formation of this basal magma ocean. And this is really interesting because this shows the compressibility of magma at high pressures. So what we're seeing here is, basically just that, how compressible this magma is. And this has implications for planet formation and planet evolution models because you could end up storing a lot of volatiles if you have a volatile-rich magma within the mantle under this solid rock layer where you aren't able to really get any of these volatiles to escape. So, going back to looking at this density radius plot. If we end up plotting our curves onto this plot, you'll see the 3 different colors and then the model as well. You'll notice that it kind of looks curved, so you've got this population that kind of does this basically this S curve around the rocky planets. And you'll also notice something interesting. So these magma ocean planets, lava worlds, are degenerate with essentially the solid composition because the precision that we would need to tell the difference, we just don't have currently with our instruments. And so, so for planets like this, maybe we could be able to tell a difference, but for the majority, we're not. And also for these extremely low density planets, magma can't explain them alone. So we need to do some other work to figure out why these planets are so weird. So I will leave you, no, I'm joking. We could say all of these different things. These are the main takeaways that you could take from this talk, but I won't do that to you guys. I'll leave you with just a few. So host star abundances are a great way to inform planet formation models and planet interior models. And then a couple of results that I'd like you to take with you is that we see this metallicity cliff for these super Earth planets. And that's very interesting in terms of planet formation and asking this question, how much material is required for planet formation? And for these low density lava worlds, we cannot explain their low densities due to magma alone. So they could be coreless planets or something quite exotic, but we need to do a bit more to kind of figure out what's going on here. So with that, I'd like to thank you so much for having me, and I'd be happy to take any questions.
That was a great talk, Kiersten. Is this working? Test. Okay, it's working. Kiersten, that was a great talk. Yeah, so we have time for questions. So if you don't mind speaking into the mic, just so people online can.
Sure. Okay. Yeah. So it looked like maybe almost all the planets in your like metallicity comparison all had maybe orbits shorter period than 10 days. Is that about right? So I mean, it seems to me that maybe, in addition to planet formation, there's also migration, and maybe I think most ideas in planets, in orbits like that they didn't quite form there. Maybe for some of the M dwarfs, maybe, but it seems like it could be it could be very different at much wider orbits, and maybe some of this effect just has to do with migration.
Yeah, so that's something that could occur. The difficulty with migration for these low metallicity stars is that the disk lifetimes are significantly shorter, and also you end up having smaller disks as well. So it definitely could be a thing that we should look into, but those are also some of the difficulties with thinking about this metal pore regime and kind of the intricacies of what happens within the disk, for sure.
All right, yes. Also, if, oh, okay, yeah, sure, I'll come to you in a second. And if folks online have any questions, please feel free to post them in chat or raise your hand, and thank you.
Thanks for interesting talk. So I'm interested in the relative contribution of radiogenic effect versus the tidal effects, because some of those planets can be old, some of them can be young, right? So that's probably the interplay between those two factors that can play a role, and also metallicity, as far as I understand, drives the has different efficiency of convection, right? That basically removes the heat flux from the so is that also taken into account in the model that you use?
So our model doesn't take into account any sort of dynamical effect. So the way that we model it is basically from the surface temperature of the planet. So we're accounting for basically these lava worlds, and I agree. I even talked with my advisor about this. I was like, should we do something with, there's induction heating, tidal heating, and all of these other things, which I think are very interesting routes to go down. And I was also talking with Joe earlier about how this could be a very interesting thing to look at. But no, we haven't, and I think that's a very interesting thing to account for.
Mm-hmm. Thank you.
Thank you for the wonderfully clear talk, and I also appreciate how beautiful your slides are. I was wondering, because I'm thinking towards Habitable Worlds Observatory, and it's been a long time since I've had my grad school galaxies and stellar classes, but I vaguely remember that, the nearby stars are going to tend to be more, metal rich than these halo stars that you're looking at. But I'm wondering, are there any implications for your results for the population of stars that we would be trying to find planets around with Habitable Worlds Observatory, which would be focused on, nearby stars?
Yeah. So you could hire me, but this is actually one of the things I'm thinking about in terms of postdoc proposals. But one of the things that I want to look at specifically with these two samples, as well as a sample that I'm looking at now, it's 144,000 stars, is basically trying to figure out where we expect planets to form, and then particularly for rocky planets, how much water they can store within their mantles, because even if you get water deposited on the surface, that doesn't mean that it's going to stay there, and looking at water cycling evolution of these rocky planets. So one of the things I'm thinking about is basically trying to figure out where are planets forming, first of all, what do they need, and if they have the stuff that we expect that they need to form, how are they going to evolve if they get enough water, which is, a rocky planet acquiring water is a very difficult thing for formation models to constrain. But if they do have enough water, does it go into the mantle? Does it get stored into the mantle, or does it stay on the surface, or, is it lost to space? So very interesting question, and it's something that I'm planning on looking at.
I also want to add to this question. that Jad asked, that's the stellar component. So you mentioned the planetary component, but the stellar component is equally important, specifically on these stars that are in halo, that low metallicity stars. And we know that the low metallicity stars drive low efficiency convection. Low efficiency convection drives low efficiency magnetic fields and low efficiency activity. So this how they may be related. So, and we might need activity in order to drive some, habitability. So this stellar component is extremely important here too.
Oh yes, and it's actually very interesting too. I will stop talking about this in a second, but it's really interesting that you mentioned metallicity, because from protoplanetary disk models, lower metallicity, you end up getting more water. But as you increase the metallicity, you end up getting less water formed in the disk. But you also get more minerals that store more water, which could mean that these more metal-rich planets that you would expect to have, magnetic fields and things like that, maybe all of their water is stored within the mantle, because now you've got minerals that store a lot of water as well. So do they even have surface water? Which is, one of these questions that, once again, I want to answer or try.
Right. Thanks.
Hi. I was just wondering, these planets and host stars that you're looking at, the population you're looking at, are they mostly like in the solar neighborhood or nearby, or are they are they closer to the galactic bulge, or do you think the distance from the bulge has an effect on metallicity or planet formation?
Yeah, so there's definitely an effect between, kind of where they're located at, especially as you start to move away from the plane. I'm not quite so sure specifically moving away from the bulge, but I would assume that also has an impact. But we see that as you move from the plane of the galaxy, you have a decrease in planet occurrence rates. But the sample that I was looking at, it looks at decently far away stars. So think about like a kiloparsec. So not as great detection efficiency on those, right? But we are able to get some detection efficiency, but the majority of our stars are around 600 parsecs. That's like the average. So pretty, not super far away, but this is partially due to tests. Specifically, we're not able to get really good detection efficiencies on stars that are, really, really far away due to TESS's aperture. But maybe with some of these other, surveys coming online, like I know Roman, some people have been talking about potentially using that, and maybe we'll be able to see a bit further out. Actually, we'll be able to see pretty far out with Roman, so yeah.
Hi, really good talk. I learned a lot today. I actually have a question when you're talking about the first part of your presentation, when you talk about like the occurrence rates and everything. So you did mention that you're basically detecting transits, and I was just wondering how was the pipeline that you use for detecting transits?
So I essentially made the pipeline. So basically we use these FFI. We basically get the FFI data from Eleanor, and then we end up using Wotan as well as transit least squares to do our detrending, and as well as some sigma clipping code that I've written myself. And then we use Eddie Vedder basically as the primary vetting software before we end up doing follow-up observations on it, as well as having a couple of different criteria in terms of the basically matching of the transit duration to the stellar density. But happy to talk offline about everything in terms of that.
Yeah, I'm really curious about it, so later I'll ask more questions.
Yeah,
Thank
of course.
Great. Does anyone else have any other questions in the room or online? All right. Oh, just people saying great presentation online. All right. Well, let's thank Kiersten again for the great talk. And Kiersten's around this afternoon if you want to meet with her. We're also going to go grab lunch, and anyone's welcome to join us. So just meet up after the talk here, and we can talk about that. But thanks, everyone online, for joining.